First one is going to be looking at an analysis of looking at the size limit in the commercial halibut fishery. There's been a lot of discussion over the last several years about the potential for changing the size limit. Will that allow us to take any advantage of small fish that might be present in the population? And the second set of presentations will be on harvest policy considerations and an update on where we're sitting on the management strategy evaluation. So I'll ask Juan Valero to do those presentations, please.
Hello. So this presentation will focus on analysis on potential effects of potential changes to the current minimum size limit in the commercial fishery for Pacific halibut. And just as a note, if you're looking for material relevant to this talk, is in page 195 of this year's SORARA or page 22 of the blue book most of you have in your hand. So as a brief history of the minimum size limit, all of you know the current minimum size limit for the commercial fishery is it's 32 inches, or it's equivalent of 81.3 centimeters. But that has changed through the history of this fishery. From at the beginning of the fishery in 1988, the commercial fishery, to 1943, effectively there was no size limit. Starting in 1944 to 1973, sorry, the minimum size limit changed to 26 inches or 66 centimeters, and the current minimum size limit of 32 inches or 81.3 centimeters has been in place since 1974. As you just heard, we've had requests to staff to evaluate the potential effects of lowering the size limit. So among the rationale for those requests of analysis for lower the size limit can be counted the fact that for Pacific halibut, females tend to grow at a faster rate than males. What we have here is halibut size by age. As you see, the females are growing faster, and when you have a minimum size limit, which is this line here, that effectively means that a female for the same age will have a higher probability of being caught if selectivity is based by the size of the fish. And I will define very briefly here selectivity, and you have a definition of that in one of those pages that were provided to you with definitions. Basically, selectivity is the relative probability of a fish of being retained or landed by any of the fisheries based on its properties such as size, if you assume that selectivity is at size, age, or other characteristics of the fish. That's what selectivity is. As I was saying, the fact that females grow faster than males, effectively what it means is that when you have a fishery on it, you are removing them at a quicker pace than males, because males grow at a slower rate. So effectively what you expect to see in that case, if we have here the proportion female on the population between 0, that is no females, and 1 of females, is that for the younger ages, the proportion is expected to be about half and half. And then since you're fishing mostly on females, that proportion begins to decline with age until you basically what you have left for older fish are mostly males. And that gets translated, if you will, into what we see, or we estimate to see on the commercial catch, the proportion female on the commercial catch. That is, for younger fish, say ages 6 to ages 10 or 12, most of them are actually females. There are very, very few males that are caught of those ages. This gets compounded by ongoing declines in size at age. That is, if we had to measure the changes in size for each of the ages, or the growth, if you will, of an average female, post-white female, if you will, in 2002, we would have gotten basically this curve here. By 2011, it had come down, and the same thing for males. Another aspect of the rationale has been the estimates of very large and increasing total biomass that is composed of halibut ages 8 and plus. This is estimated by recent stock assessments, and effectively is estimating that there's lots of fish out there that are small or young. This contrasts with recent declines in trends of eBio. These are both estimates from recent cost well assessments at the cost by level. And this contrasts also with the ongoing decline on the data itself, which is the survey data, which has been a continuous decline since the inception of the survey. So this difference between a declining estimate of eBio, declining survey, but an increasing estimated trends of TBio have prompted also requests of, or perhaps there's a way to safely tap into those total biomass. So how can we actually go about estimating the potential effects of changing the minimum size limit? Well, there are many of them, and they all are going to be mainly based on what we assume is going to happen with selectivity. That is, every time we're going to do something with the minimum size limit, then the fishery is going to be potentially or most likely prosecuted in a different way. And if we're talking about decreasing the size limit, it will mean effectively that smaller fish are going to start to be retained. So among the approaches we follow, the first one was the one that makes the least assumptions. It's just to look at effective female selectivity and maturity at age, and this is based on life history theory. The second one is straightforward single area yield per recruit and biomass per recruit. That involves making more assumptions and modeling. Then a migratory yield per recruit and biomass per recruit analysis. This is similar to the one area, but now has multiple areas and migrates fish. So again, makes further assumptions. So in terms of that important process, selectivity, and what assumptions can we make when we're changing or evaluating changing the size limit, what we have here is that selectivity between 0 to 1, halibut size, here is 81.3, so that's the current minimum size limit. And what we have here in the open circles is the currently estimated cost-wide commercial selectivity. In black is the currently estimated cost-wide survey selectivity. So those are the estimates that we have for that come up basically from the data and for the modeling of the assessment. So this one that we have here on the left is assuming that a change in the minimum size limit effectively by lowering pretty much to the extreme with the current type of gear that we use, it will result in a large change towards smaller sizes in the population. So that's basically the assumption that we make for this extreme case, if you will, for these three approaches. The other assumption that will entail changes in minimum size limit is that the fishery, instead of actually have this type of current selectivity, will shift to the selectivity that we currently estimate for the survey. That is, assuming if there's no size limit or the size limit is smaller, the commercial fishery may fish to something similar to the survey. The other approach is to actually estimate or to come up with gradual changes in selectivity as a function of gradual changes in minimum size limit. And again, the further down we go, the more assumptions we have to make regarding how selectivity and other processes are going to change. Here we can try to model those, for example, by assuming that those gradual changes in minimum size limit will result in an increase in the selectivity of fish below 90 centimeters. This will be, for example, if there's less shaking in the commercial fishery because you can now keep smaller fish, but larger fish are going to remain selected as they are now. That's what we call pattern A. Pattern B is actually shifting gradually the whole selectivity curve to the left. So that is assuming the shape doesn't change. The only thing that it changed is the proportion of all fishes relative to their size that are going to be selected to the gear. And this will be, for example, if changes in size limit will be accompanied by changes in hook size or hook spacing to target the smaller fish. Into the first approach, again, those are the selectivities that we've looked at. Just look at the current situation, or if a change in size limit will entail a change in selectivity to that of the survey or that commercial shift to the left. what we compute after this selectivity at length is the effective selectivity at age by using average coast-wide size at age. And this is only for females. The focus of this part is only on females. So what we see here is like, well, this is the effective selectivity at age in the current situation. If we actually fish, the commercial fishery were to fish like the survey, that one with solid dots there. If we were to fish like a shifted commercial, is the one on dotted lines. So the point here is to compare, if you will, how quickly a female starts to be selected to the gear with respect to the available estimates we have for female maturity. So every time that a curve is going to be to the left, it's meaning effectively that we are catching immature females at a faster pace than they are maturing. So effectively we're catching more immature females in this situation than if we were to be in the other case. So this is only for the coast-wide situation. As we know, we have several areas and different areas. In this case, I'm just pulling all of Area 4 into one big blob to make the presentation shorter. And each of these areas have differences in size at age. That means that these selectivities at age are going to be different for each area. And that's what we see in these plots out here. So each color that you see here, the green, the orange, the blue, correspond to this map for those not familiar with the geographic scope of our fishery. So in the current situation, the estimates of commercial selectivity at age effectively show that for area 2 in particular, we have capture, in the current situation, we have some capture of, or we're expected to have some capture of immature females, particularly above age 11. And then other areas such as, for example, area 3 and most of the part for area 4, we are starting to catch those fish in the commercial fishery after they mature. If we were to fish like the survey, effectively what this does is to shift those selectivities to the left, so there's an increase in the capture of immature females. And if we were to, basically for all of the areas, and if we were to, if the change in size limit were to result in a shift to the left in selectivity at age, effectively that will mean that we will be catching for most areas females at about 3 years before they mature for all of the areas. Again, this is based on these calculations of selectivity at length and selectivity at age and doing it by each of the areas. The other way to look at this, that actually makes less assumptions, is instead of modifying those estimates of selectivity at length and at age, just look at the raw landings. And this is a cumulative plot. So effectively what it does is calculates how quickly you reach the age by which you catch all of the fish of that age. So effectively this is an analogous, if you will, of selectivity. So in the case of the commercial fishery, in this case it's year 2009, again, maturity, female maturity is in black. So we see that for areas 2A and 2B, we are catching a larger fraction of immature females than in the other areas, for example, most of area 4 and area 3A. And you saw some of this in some of the plots that Stephen here has presented in past stock assessment presentations, and you see an example in his presentation today as well. So if the fishery, commercial fishery were to fish like the survey, this is what it shows here, again, female maturity in black, that will entail now that a larger number of areas will be expecting to catch a larger fraction of immature females. This is basically this part of the curve here. And will be protected, if you will, first to be mature rather than being caught, only for area, in this case, 3A and 4B. Another way to look at this, and this again making the least possible assumptions regarding changes in what changes in minimum size limit may do in the future if we were to follow that route. Rather than doing it through modeling, we can just look at the past. We've been there before. So we had, as I mentioned before, a period of the early inception of the minimum size limit. So it will be years before that plot here. And as we see, the proportion of immature females, in this case we cannot tell actually if they're females or males, so these are both sexes combined, but since males still were expected to have been growing at a slower rate than females, probably it's expected that most of these proportions were females. Effectively, the maturity curve, the female maturity curve, it lies to the right of the commercial landings at the beginning of the current size limit. In a period with a size limit of 66 centimeters, again, most of the landings were outpacing female maturity. And in the period of no minimum size limit, as we can see here, it was the most extreme of all cases. That was about immature females were captured at a rate or retained a faster rate by about 4 years before they mature. An important caveat needs to be made here is that the estimates of maturity, the female maturity we have, are the ones that we use for the assessment, and then the ones for the recent decades. We do not have similar estimates of female maturity for, say, the earliest years. Second part of the analysis is the yield per recruit and spawning biomass per recruit. I will not go much into details, but just suffice to say that going from the coast-wide selectivity at length, then we need to compute coast-wide selectivity at age for both sexes, blue and pink, and also for the different selectivities. So we'll jump straight into the results for timing. This is to illustrate that if we were to continue to use the current harvest rate, which is here 0.215, this is basically the status quo of where we are now, and these are under the two different assumed selectivities. So if we were to stick with the same harvest rate and shift the selectivity to capture smaller fish, and we can see here what the impact will be. So if we were to fish, if the commercial fishery were to fish like the survey, we see that will be actually a decrease on the yield per recruit. That is how much poundage we're getting for each fish or each halibut that recruit to the fishery. So it's a slight decrease of about 3%. And actually, if we were to fish drastically to the left of the commercial fishery at present, that will have an increase in yield per recruit of about 14%. But these, as most things in life, come with consequences, and the potential pros here come with a drastic reduction in the level of protection to the stock. So a way to measure the protection to the stock is to calculate what is called spawning biomass per recruit. That is how much a recruit will contribute to spawning biomass through its lifetime. And as we see, the current situation allows us to be at a place that we protect 37% of that biomass that will be expected if there were no fishery in a virgin state or state or unfished state. So that's the status quo. So if we try to protect the spawning biomass by the same amount we are doing now with the current size limit and harvest rate, is the analysis that was going to be next. But if we just stick with this harvest current target harvest rate, effectively that would mean that rather than being at 37% of unfished, we were expected to be at 31 or 17, which is protecting, in this case, the spawning biomass by 47% of what we're protecting now. And that's effectively what I said here, so I will not go into that. If we constrain the analysis to actually have the same level of protection, so now we ensure that whatever we do, we protect the spawning biomass at the same level. Effectively, what this shows is that we will have to have a precise control of lower target harvest rates, because we're fishing at smaller fish that will have produced more spawning biomass had we left them in the water, so we actually need to exploit them at a lower rate to be able to result in the same level of protection. And even if we do so, the yield per recruit is expected to decline by about 10%. So there's not much to gain by even protecting the same level of biomass per recruit. That's basically what I just said here. The other part of the analysis, this is again on the yield per recruit part, is to look at what the proportion female will be expected to change, or will it change or not by much if we actually change the minimum size limit and therefore the selectivity of the commercial fishery. So as we said, as I mentioned before, these white dots are the current case by which in the population the proportion female decreases rapidly with age, and that's the harvest rate that we are using on the stock, or with the target harvest rate that we have for the stock. So if we were to fish like the survey, we see that the proportion of females still declines rapidly with that survey selectivity, and although you have a large change, a relative change, say for age 25, it goes somewhere like around 12% females left in the water by age 25 to about 21%. So it looks like a big change, but still the proportion female in the population is relatively small. And that will entail, again, a smaller, lower harvest rate. So this case will be the case that will be expected if there was no fishery. That is 50% females and males, assuming they have the same natural mortality, so on and so forth. So the only case where we get an increase in the proportion of female by several ages, or by older ages, is if we were to use a target harvest rate of about half of where we are now, and in that case the commercial shift, or the commercial selectivity shifted drastically to the left. This will still entail the capture of immature females, as we saw in the previous analysis, so a precise control of that lower harvest rate will be paramount in that case. Still, the proportion female in the catch will be the highest under these two scenarios, and again, in a similar case, the proportion of female in the catch will decrease, but only if we fish precisely at a very low harvest rate and with the risks that entail. Third part of the analysis is the migratory yield per recruit and biomass per recruit. It's the same approach as before, but now we incorporate these 6 regulatory areas, again pooling area 4 for expediency. For those not familiar with, or those that are familiar, but just a reminder, the predominantly direction of migration is as shown here, predominantly going from the north to the south. And if you want to read more about it, Ray Webster has a number of reports in past years, and we have a report in this year's RARA. And effectively, migration was modeled in this case following 2 scenarios. One, assuming that halibut of all sizes move at the same rate. That is what I call the one migration matrix assumption. The other one is taking into account the evidence showing that smaller fish move at different rates, typically faster than larger fish. In this case, this is what it shows here. This is yield per recruit for all of the areas, same as here. And what we see in the white columns for the case with one migration matrix, that's effectively the status quo. So that is for each recruit, each coastwide recruit that the population gets, this is how much yield for that recruit that each area gets. So most of the yield per recruit gets accrued into area 3A in this case. That's the case for the coastwide when you sum the one for all of the areas. So if we were to fish like the survey, as you see here, for all of the areas and for the coastwide case, there's a reduction in the yield per recruit. In this case is when we are taking into account the fact that we need to have the same level of protection at the status quo. So for both cases, fishing like the survey or fishing like the commercial shift results in a reduction on yield per recruit, and also in some changes in the distribution of the proportion, basically the spawning biomass per recruit per area. So I will not spend much time here for time reasons. If we use a different migration matrix, in this case the one different for juveniles and for larger fish, we see the distribution of yield per recruit changes from the previous case, but overall results are the same when you constrain the analysis to have the same level of protection as the status quo on the spawning biomass. There's a decrease in the spawning biomass per recruit, and the harvest rates that will have to be applied are very similar to the case of the one area, and again are lower than the current target harvest rate. Last part of the analysis is the one on gradual changes in selectivity and minimum size limit. As I mentioned before, two patterns. Gradual shift A assumes that most of the changes in selectivity will, most of the changes in a gradual change in minimum size limit will affect the selectivity of smaller fish only. And pattern B, which effectively assumes that the shape of the whole curve shifts to the left. And this is very busy, so I'm going to take some time to explain some of these panels and what they mean. This is basically the basic detailed output that you can see in the Blue Book and RARA documents, and these are basically isoplates or curves that have the same properties. So what we see in this axis is harvest rate, and what we see in this axis is minimum size limit from 65 centimeters to 85 centimeters. And the thing to look at here is if you have things that occur in parallel or results that are in parallel, it means that there hasn't been much change from changing the size limit or the harvest rate. And what you need to look at, what is parallel and what is perpendicular or across the lines, if you will, are for these crosses here. This black line there is the status quo condition, that is a size limit of 31.3 and a target harvest rate of 21.5. And the crosses there are those combinations of minimum size limit and target harvest rate that will result in the same protection to a spawning biomass. And that's effectively what you see here. That's the panel of the percentage spawning biomass per recruit relative to virgin. So since we are controlling for that effect, obviously it's going to be parallel to it. So this plot only shows that. There's not going to be an effect of changing the size limit on this variable because we're controlling for that not changing. In terms of yield per recruit, again, that's the status quo. And as we see, by reducing the by reducing the minimum size limit and therefore reducing the target harvest rate, we see that this line starts to cross those lines of yield per recruit. And as we see, we go from something that is above 3.75 to something that is about 3.5. So effectively, we're going across the lines, and we are reducing yield per recruit under this assumed selectivity. In the case of average female age, reducing minimum size limit actually do not cross any lines, but it's going towards that direction. And it's the smaller the minimum size limit is, the larger the average female on the ocean is, but it's relatively small. It's a change of about 4%. Then in terms of the average weight of the catch, as we can see here, the status quo is here. If we start to decrease the minimum size limit, effectively we're crossing the lines again, and that means that as we lower the size limit, we're going to be having or expecting to have a smaller average weight of the fish in the catch. So going from something around 25 pounds at present to as lower than 20 pounds if we were to go down to 65 centimeters. In the case of the change in numbers in the catch, that is how many fish are going to need to be handled comparative to the status quo. It will mean that as we go down, again, we're crossing the lines. So for example, here it will mean this is 0, this is the number of fish we're handling under the current situation. If we lower the size limit, effectively it will mean that we will have to handle, in this case, up to 30% more fish. In terms of discards per recruit, those are going to decrease because we're going to be keeping some of the fish that now we are discarding and dying. But again, even if it's crossing the lines, the effect is very small. So it's around from 0.25 pounds per recruit to about 0.1 or a little bit 0.1. So that is about less than 10% of the yield that we get now per recruit. So I explained those panels in the previous thing, so I will not spend that much time with this selectivity shape, but suffice to say that, again, we're actually a little bit crossing a line here, and it's meaning that at an extreme, under these selectivity assumptions, we're going to be, again, losing yield per recruit if we lower the size limit, and suggest that at most, here on this part of the curve, we will gain about 3% of yield per recruit by lowering a tiny bit the size limit. Again, under all of the assumptions we're making about these selectivities, and again, entailing a lower harvest rate, target harvest rate that we currently have. So again, the changes in the average females in the ocean are in the order of less than 10%. The average weight in the catch will decrease. Similarly, the number of the percentage change in the number of fish that need to be handled will go is expected to go up by as much as 60% from where we are now, and again a similar pattern for the discard per recruit. So another thing that we want to highlight here is, well, if it is so hard to predict how selectivity is going to change to in relationship to the minimum size limit, perhaps monitoring our landings can inform us in the future about how that selectivity actually changes into the future, rather than trying to predict it and then potentially failing to meet that prediction. And to do so, I would like to come up landings data we have on the, in this case, the percentage of commercial landings that lie below the current minimum size limit. That is the percentage under 32 inches, and then the fraction by size for each of the areas of, that we manage. So again, for example, in this case, for all of the plots, that's the minimum size limit. And what we have here is the percentage that is currently landed. In this case, this is for 2008. That is below that size limit that has been in place for several decades. So as we see, it goes from a high of almost 9% in 2A and about 8% in 2B to as low as less than 1% for areas in Alaska. Overall, coast-wide, 3.23% of the landings are below the current minimum size limit. So the thing is that here, the point that can be made here is like, well, if we actually had observations, precise observations or monitoring of the landings for each area, then we could actually know how a current or future size limit may actually affect the landings and therefore selectivity. However, in the only area that we actually have a full monitoring of the landings, which is in area 2B, is one of the ones that actually has the largest percentage of undersized fish. So if the catch is monitored, but the enforcement of the whole system is actually not providing necessary incentives to actually have this number to be small, then we cannot expect to be able in the future by similar monitoring to know how selectivity may change due to changes in size limit. Finally, into one of the other parts of the rationale for moving to a lower size limit, as I mentioned before, it is based on the large and increasing estimates of total biomass of fish age 8+, and that being estimated to be different from the declining trends that we see or we estimate on eValue and that we see on the survey weight per unit of effort. And as you're going to be seeing in the next presentations, we have the recent assessment has something that is called a retrospective bias, that is estimates of early biomass, both for total biomass and explorable biomass, that are estimated to be high when they're first looked at. Then it takes us several years later, several assessments later, to actually find out that the level may not have been that high and that the trends could have actually been different than what they were estimated at the beginning. So under the current retrospective or ongoing retrospective bias that we've seen in the stock, at least in 2006, that resulted in overestimation of biomass and the reversal of those increasing trends. This again brings a word into caution about the potential impacts of dropping the size or changing the size limit under those circumstances. A quick summary, those are the approaches that we follow for looking at the potential changes in size limit. The first one, as I said, in terms of female selectivity and maturity at age, what we found was that, actually was found before, which is highlighted here, with the current minimum size limit, areas 2A, 2B, and 3B have a larger capture of immature females than other areas, and further lowering the minimum size limit is expected to increase the catch of immature females up to 4 years before they mature, and this is based both from modeling results of assumed selectivity, but also looking at the realized selectivity, if you will, from historic periods with different or basically smaller minimum size limits. Under those results, lowering the size limit is not expected to be a precautionary approach based on life history theory. This is basically a common sense, but it's also works that show this through simulations, is that it is a precautionary thing to allow females to reproduce at least once before they start to be caught by the fishery. The yield per recruit analysis and biomass per recruit show that using the current harvest rate and lower selectivities for the commercial gear or shifted to the left would result in a reduction of the level of protection to the spawning biomass to about 82% and 47% of what we are expecting to get with the status quo. If we constrain the analysis to actually provide the same level of protection to the spawning biomass, then the target harvest rates will have to be precisely controlled at lower levels than we currently have, but still it will result in about 10% lower yield per recruit that we're getting now from the stock. The migratory yield per recruit and biomass per recruit is very similar results to the single area, and it also showed the level of protection is actually changed, is different for different parts of the coast, and is expected to be lower in area 2 than in area 3, and this is consistent with past widget results that you saw over the years. Finally, the analysis on gradual changes in selectivity and minimum size limit suggests that or indicates that reducing the minimum size limit will result in a reduction in yield and spawning biomass per recruit when we are controlling to have the same level of protection. The only increase in yield per recruit that we get is at most 3%. It will require precise control of a lower harvest rate, and at the extreme, if we were to lower the size limit significantly to the left, still the females are going to be predominantly in the catch, and that will result females in the population overall to change at most from 44% to 45% for ages 6 and older, and the largest change will be in age 25. That will be going from 12% in the population to 22% in the population. So not much of a change in that variable. As a conclusion from this analysis, it can be said that lowering the minimum size limit is actually not supported by the analysis we have at hand.
Thanks, Juan. I just let Juan have a drink here for a second before he moves into the other presentation. This was a fairly complete analysis of the minimum size limit changes, but we wanted to give you the benefit of both looking at this from a different analytical perspective as well as showing you a number of different metrics about how the catch might change and the characteristics of the catch might change as we decrease the size limit and whether selectivity goes along with that.
Yeah. Okay, charge here. Just change something.
We will take a break after the next presentation by Juan.
Okay, so continue. Okay, so this is a continuation of the work on harvest policy or harvest strategy for this year, and these are going to be 2 presentations, one after the other. The first one is on harvest policy consideration focusing particularly on retrospective bias and its effect on the harvest policy and biomass projections. The second part will be on an update of the management strategy evaluation or MSE. And for this part of the presentation, you can look at page 59 of the Blue Book or 311 of the RARA, and you're going to see the reports and figures that I'm going to be presenting here. Okay, a brief look in time into the recent history of what the target harvest rate has been for the Pacific halibut fishery from 1984 to 2011. As we see here, that's the target harvest rate year, and that's the level. We see that it has changed between a high of 35% of explorable biomass in the mid-80s to as low as 20% in recent years. This is, if you will, the target harvest rate that is determined for the core areas of the stock. This last increase here is just due to a change in the definition of eBio, so it's not actually a change in the target harvest rate, but it's a change in the definition of what eBio means, and that's work by Stephen from last year. There we go. Thank you. As I mentioned, that's the target harvest rate for core areas since 2006. There has been the determination of what they're called areas of particular concern based on trends of indices and estimated status and conditions of those areas. And effectively, the target harvest rate has been reduced for those areas, 4B, 4CD, 4A, and 3B, from that overall level of 20% to 15%. So that's in terms of target. That's where we are shooting for every year we do the assessment, recommend quotas, and so on and so forth. Okay, in terms of our ability to meet those targets is something that is called realized harvest rate. So the target is what we shoot for. The realized harvest rate is a realization each year of how close or how far we were from that target. And what we see here in the white columns are the most recent estimates of cost-wise realized harvest rates. So as we can see here, this is from the start of the recent assessment to effectively 2011. And as we see, there has been estimated increase in the realized harvest rate since the start of the assessment up to a high in 2008, where the most, basically the current estimate of realized harvest rates for 2008 was around 38%, and the target was around or less than 20%. Since 2007, with the implementation of the cost-wide assessment, this slope, if you will, has been declining each year rather than increasing, but as you're going to see on the following slides, the actual level for all of this year has been changing. The figures you saw before were in terms of cost-wide realized harvest rates, so increasing the target somewhere around a little bit below 20%. We don't have a cost-wide target. It's just the summation, if you will, of the area-by-area cases. So this is the most recent estimate for each of the areas. That's the target harvest rate there. And as we see, for effectively all of the areas, we have departures from the target, and for all of them or most of them, we have departures that are above the target. So the most current estimates of realized harvest rates over the past decade have been above the target, and in some cases, like for area 2C and 2B, about 2 to almost 3 times as high as the target. As I mentioned before, those areas were determined to be areas of particular concern during the past decade, and the target harvest rate has been reduced to 0.15 instead of 0.20. So how do we get these departures? I mean, where are they coming from? Well, part of these departures come from what are called misspecifications in the model. So things we are not controlling for when we are actually setting catches. Part of that come, and you are all aware of this, because this is what basically prompted the change from closed area assessments to coastwide assessments. So this is the view that we had of the stock in 2007. This is a sequence of closed area assessments or different closed area assessments for each area by then. So at that time it was estimated same or similar increases but realized harvest rates, but the actual level itself was much smaller. So it was departing at most 2 eyes, for example, for area 2B. At that time, in 2007, it was evident, or actually before that, that halibut were continuing to migrate. Therefore, the closed area assessments were biased, and a new way to assess the population was developed, which was the coastwide assessment. In the 2007 version of that coastwide assessment actually indicated that the realized harvest rates have been much in excess than what was predicted by the closed area assessments. For example, for 2B, we were here from being about twice as high, or basically, yeah, from 20% to 40%. This, in 2007, it was estimated by the coastwide model that it was about 60%. That's for areas effectively 2. For part of area 3 and area 4, it was actually the opposite, and the estimated realized harvest rates were smaller. So the misspecification in this case of the assessment model was actually due to the unaccounted for halibut migration. When accounted for by the coastwide assessment is that we got these different estimates of realized harvest rates. However, since 2007, if we look at the realized harvest rates for each area and also coastwide, we see there has been an upswing on the realization of what those realized harvest rates were. And as I mentioned before, in all cases, they have been estimated to be, or they're now estimated to have been higher than estimated originally in 2007. And in this case, part of the problem is the underestimation of harvest or target harvest rates at the moment of doing the year assessment effectively, and of the underestimation of the harvest rates of past years as well. That resulted in an overestimation of exploitable biomass, and this is an ongoing retrospective bias. So you have heard it, and you have seen probably in the documents or in the interim meeting mentions about retrospective bias, and there might be some confusion about actually what it is. Well, retrospective bias comes from, or retrospective pattern or problems come from the fact that each year the stock assessment estimates not only the most current assessment biomass, for example, 2012 biomass, but also estimates or re-estimates exploitable biomass that were initially estimated in past years. So it allows us to have only one look at the current estimate of exploitable biomass or the other biomasses, but it has several looks of biomass as estimated in the past. So retrospective bias occurs when the historical biomass series is consistently overestimated or underestimated. That is, the retrospective bias occurs when we realize that what we thought we knew in the past, actually it is not. It has been overestimated or underestimated. In our case, the recent stock assessment for Pacific halibut had consistently overestimated biomass and underestimated harvest rates, as you saw in the previous slide, due to this bias. An example of what it is, not in words but in pictures, is to look at past biases or similar biases for halibut and other fishery resources, and some of this is, most of this is discussed on the reports if you want to read more. But this is something that has been observed on assessments for Pacific halibut. In this case, this is for area 2B, British Columbia, estimated exploitable biomass in millions of pounds from 1975 to the assessment in 2004. So if you take, for example, the assessment in 1997, that was the first time that it was estimated that eBio there, and then in the following years, each assessment that came back estimated that initial estimate actually was a high estimate, because the most recent estimate suggested that I was coming down. So just to put it into the context, the first look that was done for the eBio on 2007, by which catch limits were recommended for, over the subsequent assessments was estimated to have been actually much lower than originally estimated. So this is a case basically of concern, if you will, on retrospective bias. Another case, the retrospective pattern, this is again a closed area assessment for area 3A of Central Gulf of Alaska. If we take the same years, 1997 here, that was the first time that it was looked at it, and subsequent assessments then went, it's hard to see here in the slide probably, but it went up and down from that value. So there are some trends like 95, 96, 97, 98, 99, 2000, and then it comes back up. So effectively, if you follow what happened to 1997, it was estimated to change at some point, but the most recent assessment at that time, 2004, actually estimated to, the estimate of 1997 by the assessment in 2004 was actually close to the one originally made. This is not, hasn't happened only for Pacific Halibut, but for other fishery resources. In this case, it's probably one of the most famous cases of retrospective patterns, and actually the one that probably brought this issue into attention for fishery management, which was retrospective issues on northern cod assessments and its effects on projections. So what we see here are these blue dots there were the first look at the E-value of that year, in this case by an assessment in 1980 and the estimate for 1980. And what we see in red here is the most recent at the time, what is not actually the actual stock, but it's the best estimate that was made years after those assessments were done. And that's basically the effect on the projections that those misspecifications at the time of assessment had on the process. So coming back to our case, into the recent retrospective patterns, this is based as of preliminary analysis done at the end of 2010, last year, for coastwide stock assessments for Pacific Halibut. And what we see here is that this is the case for explorable biomass, and this is, for example, for the assessment in 2006. And as you see, if you just pick one of those years, for example, that's the year, the estimate that was used to recommend catches and so on and so forth. And as newer estimates of that year came in subsequent assessments, it actually came down. So as of the end of last year, this is how much the most recent assessment as of the end of last year was showing to have departed from the initial estimate. So a point that I want to make here also is like the solid lines here are the actual estimates of the trajectory for each past E-value. What we have here in dotted lines are the projections, assuming that the last year of the assessment and the first years of the projection is actually correct, that it has no bias. So those are the projections, assuming that it has no bias, has those projections in there. But this is as of last year. In this case, this is the effect of the retrospective bias on spawning biomass. So it's slightly different, but it's also present. This is as of this year. So this is, if we repeat the analysis of last year using the most recent assessment, we see that actually the pattern is still ongoing, and the retrospective bias, or the amount that year was overestimated, our understanding of it, increased this year. Of course, the question is that this is what happened then, and it took us 5 years to realize it. The question is, this is the estimate that we have for this year. So are we far off? Are we not biased? How biased can we are at present, as part of the questions that are at present on the table. So the previous slides were showing the retrospective bias for explorable biomass and spawning biomass. In this case, it's a retrospective pattern as of, again, last year for total biomass. And I've shown a little bit of this on the analysis for potential changes in size limit. So as we see, for example, for this case, the assessment done in 2006 estimated this trend on total biomass, an increasing trend of total biomass since about year 2000. However, subsequent assessments re-estimated that trend and actually suggested that at least part of our increasing trend was actually more recently estimated to be a decreasing trend. So the previous slide was as of the end of last year. So this is the trend as of this year. This is effectively to show that this is a continuation of a retrospective bias that has been going on for a while in our assessment, and to the extent at which it is present at now or we continue into the future, it is yet to be determined. So if we just take a different look at that data and just go in at that vertical downgrading, if you will, of the initial estimate, we can produce plots that only look at how the initial value of exploitable biomass changed through the years. So in this case, in that blue rhomboid, we have the initial estimate of the 2005 exploitable biomass that was done by the assessment at the end of 2004. And what we see is like, so catches were taken based on this value, yet in the next year assessment, that it was determined that that estimate was actually an overestimate, and that value was revised downwards. So that revision downwards kept on happening through the years for the initial estimates of 2005, 2006, 2007, 8, 9, 10, and in this case 11, although it's not shown here because this is again as a preliminary analysis of last year. If we actually take into the reduction in terms of the relative reduction in terms of the initial estimate, so we always estimate the first year assuming there's no bias, so we assume there is 1, and then we see like in the second year we look at that value that we already set catches on, we find out that it has, our understanding of it was decreased by 10%, for example. The following assessment was pretty much there, and then there's some variability on it, as you can see, but it kept on coming down for the most part. That happened for all of the initial assessments since at least 2005. So this is as of last year. So the question was, well, we had that estimate at the end of that year that is there. So it is here at that point. So this is what happened when we look at the most recent assessment and the re-estimation of the value for last year. So effectively, the initial estimate was revised downwards, so to something like 317, I believe, to less than 240. And in terms of overall bias or retrospective bias in 1 year was about 25% revised downwards. So the estimate that we have currently for the 2012 bio is in that level. And in case it will be, again, if we were to 1, and of course the question is like, well, is that estimate likely to be biased or not? Or if so, how far can we be? So the retrospective pattern affects not only our estimates of eBio and total biomass, but also our estimates of spawning biomass. And this is crucial because this is the thing that we try to protect, as it was explained in the previous presentation on minimum size limit. And it's also important because based on where we are in spawning biomass relative to fish conditions, we actually, our current harvest control rule actually makes or entails to changes into the target harvest rate to actually protect the S-bio. What we see here is the most recent estimates of the trajectory of spawning biomass as of the last assessment, or actually this year's assessment. And what we see here are what are called reference points, and this could be called like reference areas, if you will. So that level there is the estimate of spawning biomass in no fishing conditions. At this point here is, or this line here is what is called a threshold level, which is 30% of unfished conditions, and is a point that by our own harvest policy states that we should ratchet down the target harvest rate to account for that, if you will, precautionary area, if you want to call it that way. The B20% is what is called limit reference point at which the harvest policy states that fishing should stop. So as we see now, the most recent assessment indicates that the relative spawning biomass level has been estimated now to have been below the threshold level for 5 years, for 5 consecutive years from 2006, 7, 8, 9, actually, yeah, 6, 7, 9, 10. Had we known that we were at that level at the time, actually our harvest control rule has action embedded in our harvest policy, which is to reduce the target harvest rate to take into account that level of the relative spawning biomass. So this is what it is. This is the relative level of spawning biomass to unfished. Every time you follow off this green area and you go into the yellow area, effectively what it does is it has a linear decrease in the target harvest rate. The thing is that at the time we didn't know, or it was not estimated to have been that low. Had it been estimated at the time to have been that low, the harvest control rule would have decreased the target harvest rate to these values. So effectively for the year that is estimated now to have been the lowest, it would have been about a target harvest rate of 14%. Again, this is something that would have happened in the past. It didn't happen because we were not aware of it, and so the full target harvest rate was applied to that, to those years. And again, a reminder that value was not estimated that low, but it was estimated to be, again, 43% of unfished in 2006. So currently we are, the stock assessment, most recent stock assessment estimates be 43% of unfished. And the question again is that value has the potential to be revised downwards as it did in the past? That's something that is up for the discussions. So in terms of what do we do about it? So the retrospective bias is there, has been there for a while, and the way to actually get rid of it is actually to find either the causes in the current stock assessment, fix it, and get rid of the bias, and that's something that is the purview of Stephen. It's something that he's been working on, and he's going to be presenting something on those lines into the assessment presentation. Another way is actually to have alternative either assessment or management approaches that will be able to take into account that bias or that will not have that bias, and that's what I will show as part of the MSc. So, but in the meantime, what do we do? Because the retrospective bias is there, or has been there, and is estimated to potentially to be ongoing. So what I'm working here are, if you will, a way to treat the symptom if we cannot find the cure, or if we cannot find the cure as of now. That is, like, we know that this retrospective pattern has affected our ability to meet our target for past biomasses, and we can estimate by how much. So for the analysis at the end of the last year, the largest revision of any of those initial biomass that we said catches on was in the order of 30%. So a potential approach is to say, well, if we have the potential to be currently overestimating biomass by the same amount, then we should reduce the target harvest rates by the same amount to actually be able to get to those target harvest rates and not be overshooting it. And that will entail revising down target harvest rate from 0.25 to 0.15 for those areas of no particular concern. And for areas of particular concern, it will entail decreasing from 0.16 to 0.11. But that is as of last year. This year, as I mentioned, the retrospective pattern continue at about the same rate as in past years, and now we the largest overestimate of past initial estimates is in the order of 39%. So basically, that will entail that we will need to reduce the target harvest rate by that amount, and that will entail revising the target harvest rates for, to 13% or around 10%. And again, these values assuming that the maximum level of revision we have now, it is potentially what we are having this year or in subsequent years following the same approach. But we have also to make a word of caution that we actually do not know how much that initial estimate is going to be revised down, or if it is going to be revised down. But if it is going to be revised down, we can look at what happened in the past, and each year the changes in that percentage of revision actually has changed and has been larger each year. The second approach is to take at those departures that I mentioned before on the realized harvest rates with respect to the target. And in this case, this is just following two models. Stephen here is going to talk about model variance in the assessment. This is following, if we were to follow the same model fit as it was followed for the past year. And effectively, the largest departure using that model was for 2007, and that was the realized harvest rate of 32% rather than 20% that was the target. That is 61% higher than the target. So if we were to adjust the current target harvest rate to avoid similar overshootings, if this process of overestimation is continuing, that would entail revising down the current target harvest rate to 13.4 for areas of no concern, and for areas of particular concern, that will entail revising down from 16.1 to 0.10. Again, these are not reductions on the target. These are adjustments to the target to be able to reach the target if the retrospective bias is still ongoing. If we were to take another one of the model fits, again, Stephen is going to talk about different model fits for this year, then the largest departure seen so far was in 2008, and that was a realized harvest rate of 38% when the target harvest rate, or the realized, if you, or the cost-wide implied target harvest rate was less than 20%. If we assume that it was at 20%, that implies that realized harvest rates were in the order of 88% higher than the intended target. If we use that adjustment, that will entail revising downwards the target harvest rates to 11.4% or to less than 9% for areas of particular concern. Again, this is not a fix to the problem. This is just a band-aid, if you will, while the problem is dealt with. And then, as I mentioned, for the talk of current size limit, decisions have consequences or potential consequences, and a way that other fishing agencies deal with this is to actually produce decision tables that actually has a clear depiction of what things we do not know about nature and what decisions can we make, and then what is the risk that we entail when we make those decisions. So what we have here are management actions, and those are the things that we have control of. And for example, we can take an approach of adjusting target harvest rates, as for example it was shown in the previous slides, and the other management action or decision can be to continue with the application of the current level of harvest rates. And this is basically what we can do. There are things that are out there we are called states of nature, or things that we don't know that is going to happen into the future, and that's basically what is shown in these rows. So for example, in this case, some potential states of nature will be if actually the overestimation continues, or for example, if the stock continues to decline. And then other one can be, well, perhaps the retrospective issue is not present this year and it's gone away. In this case, or another way to look at this is that, well, perhaps the stock is not changing in size, or in this case, it's like, well, perhaps next year underestimation starts, and all of a sudden we are estimating less than there's out there. So based on the management action, then you can calculate both what the short-term or long-term results are expected to be, for example, in things such as yield, but also in things such as conservation concerns. So a true decision table will have, in this case, probabilities. This is just more like a contingency table, so it's simpler to read. So to read it will be, if overestimation actually continues, and again we have no control over this thing, and we actually apply adjusted target harvest rates, that will result effectively in the short term in smaller yields, because you are reducing the target harvest rate for that year. In the long term, if the overestimation still continues and the bias is still present, that will be a continuation of a smaller yield. On the other hand, under those conditions, overestimation is still continuing, and we follow with the application of current harvest rates that may result in the short term on larger yields, since you're applying the full extent of the target harvest rate. But since if overestimation is still continuing, effectively there is going to be a larger or greater implied or realized harvest rate in the future, and that will lead to conservation risk, increased conservation risk, and as was shown in the past when this thing was going on, higher than target harvest rates. So the definition of increased conservation risk that comes straight from our harvest policy, which is this is related to where our reference points are. Of course, if we make the other decision and we decide to adjust, in this case, target harvest rates, but all of a sudden the retrospective issue goes away, or actually we start to underestimate biomass, that will still result in the short term in a smaller yield. But in the long term, the moment we realize that the retrospective issue is gone, or that we actually are into a different realm of underestimation, for example, there's always the potential to return to the status quo harvest rate and apply the target rate unadjusted for a pattern that goes away when it goes away. On the other hand, well, this is not that interesting by itself, but yeah, in the case that we are applying the current target harvest rates and there's no retrospective issue or we are underestimating, that will entail to having larger yield and reevaluations of the target harvest rate. So this is all in terms of words, in terms of projections, which is the second part of this report. What we have here are eBio in millions of pounds from the beginning of the stock assessment up to the estimates for 2012, and this is estimated for the current stock assessment. So the first set of projections is what are called here status quo projections. Those are actually status quo as of last year. Those were similar to those increasing projections that we had since 2006. Effectively, what they assume is that there is no bias in the initial estimate, that the ongoing pattern of continuing reductions in size at age is going to go away as of this year, and that revisions in the estimates of past cohort strength are also going to go away. So those are the projections that we get, 5-year projections. If we actually take into account the factors that I just mentioned before, assuming not to change here, but here we're actually taking them into account. In this case is assuming that there's going to be a continuation of revisions of past estimates of cohort strength, along with continuing decline in size at age, and with revision downwards of the initial numbers of the projections. That's basically these two panels. Those are the projections for eBio if we were to adjust the current harvest rates, that is to reduce them to be able to take into account potential biases. So those are the projections, which is exportable biomass to remain, expected to remain level. And then if we were to use current harvest rates and adjusted for the patterns that are going on, assumed to be going on in this case, that will entail a continuing decline in exportable biomass. In terms of spawning biomass, again, this is the same type of figure that you saw before. And the projections is like if we are assuming that everything that has been observed in the past goes away, including the bias, size at age, and the reduction of previous estimates of cohort strength. It is suggesting a rapid increase in spawning biomass over the next 5 years. If we take into account both the potential current bias on explorable biomass and the same factors that I mentioned before, if we are correcting for correcting the target harvest rate for ongoing biases, it is the projections are expected to increase the spawning biomass to the level of the reference point threshold in 5 years from now. And if we are using the current harvest rates and those assumptions still hold, we see a much smaller increase in the spawning biomass. Of course, there are many different assumptions that you can make regarding what of these processes will continue or not into the future, and those will lie somewhere, will be somewhere in between this level, and you can look at some of those in another report in the RAR, not the Blue Book. Again, the point here is not to see which one it is correct, but the potential result of of decisions under alternative states of nature. The last presentation for the harvest policy is an update on where we are on the development of MSE, or a management strategy evaluation. And this is material that is included in page 7